So I hope you have seen that dark matter is darn important for us. Without dark matter, there would be no stars, no galaxies, no us. So now we would like to, of course, understand the nature of this dark matter. What actually is it? So there are actually very limited information we have about the nature of dark matter. So one thing we know is that it must be moving slowly. We call this property called cold. We talk about cold dark matter. Because something is hot, is moving about very quickly, but something is cold, moves about very slowly. So we call it cold dark matter. It also must be electrically neutral. If it does have electricity, then it should be reflecting a light. Because if you shine light on it, anything that has electric charge will shine it back to you. But we don't see that. So it must be electrical neutral. It also must be long-lived. As far as we can tell, even our own galaxy has a lot of dark matter in it, which means that they must survive at least 13.8 billion years. So it must be long-lived too. But pretty much these are the only thing we know about the nature of dark matter. But there are a couple of also quantitative information about it. For example, when we came out with this idea that dark matter should make up pretty much the entire mass of our own galaxy, the natural speculation was that, well, there may be kind of stars where just dim, that we couldn't see them in telescope. So some stellar-sized object, which are very dim, and we can see them in telescopes, but may be making up our halo of a galaxy. We call them MACHOs, which stand for Massive Compact Halo Objects. But even though these MACHOs may not be visible directly in telescopes, there's still a way for looking for it. And that's, again, based on the idea of gravitational lensing. So what we can do is keep monitoring, let's say, 1 million stars in a nearby galaxy called Large Magellanic Cloud. And as you keep watching these 1 million stars in here, and we are here an outskirt of our Milky Way galaxy, sometimes this MACHO may pass through the line of sight towards one of the stars in Large Magellanic Cloud. And when it does, again, it warps space, it bends light, so it acts like a lens, and that will collect more light that way. So the star you're watching may all of a sudden looking like it's flaring up, and then dims down to how bright it was beforehand. So this is called the gravitational microlensing event. Now, even though people looked for it, there was actually very few of those. And that way, we can actually limit the amount of MACHOs that would make up the halo of our own galaxy. So for typical range, or what do you expect from astronomical objects, this is 1 solar mass, 10 to the minus 2 solar masses, 10 to the minus 4, 10 to the minus 6. Then the MACHOs can be the component of dark matter only about less than 10% of it. So there's just not enough of them. Maybe there aren't them any. So it cannot be these dim stars. So now we have an upper limit on the mass of dark matter to be about 10 to the minus 7 solar masses. So that's how heavy a dark matter can be. On the other hand, if the dark matter is very, very light, then it wouldn't actually fit inside our own galaxy. And if you may know that the electron is orbiting around the nucleus, so in that case, electron has sort of a shape and certain radius, and that determines the size of an atom. In the same way, if the dark matter is rotating in the gravitational field coming out from a given galaxy, they would also give you a blob and shape of dark matter, which has a certain characteristic size called Bohr radius. So you can work this out using the law of physics called quantum mechanics. And if you're not familiar with this, don't worry about it. So you can compute, given a gravitational force, depending on the mass of a, let's say, galaxy, and little m is the mass of dark matter. This is the size of the orbit of the dark matter in this gravitational field, and that goes up as inverse square of the mass. So lighter the dark matter is, it becomes fluffy and wider spread. So at some point, it wouldn't fit in a galaxy at all. So because dark matter has to fit inside the size of a galaxy, the mass cannot be smaller than something. And that number turns out to be actually this one here, 10 to the minus 22 electron volt, if you look at the mc squared. So that gives you a range. So we know that it has to be less than 10 to the minus 7 solar masses because of this search for the gravitational lensing. On the other hand, it has to be bigger than something so that the orbit of the dark matter can fit inside the galaxy. And this is what we find. So in terms of the unit called giga-electron-volt, it has to be somewhere between 10 to the minus 31 and 10 to the 50th. So we managed to limit the range of dark matter mass within 81 orders of magnitude. And that's the progress we made in 17 years since Mr. Zwicky pointed out the possibility of the dark matter in 1930s. So the point here is that we actually know so little about the nature of dark matter. We have pretty much very little idea on the mass of the dark matter individually. Another piece of information is again a very weak piece of information. We know that dark matter sort of passes through each other in this colliding bullet cluster. So we can also limit how often the dark matter can interact on itself, namely something called scattering cross-section. Again, if you're not familiar with this idea of cross-section, don't worry about it. This basically tells you sort of the size of dark matter when you scatter them against each other, and that tells you how probable it is the dark matter would get scattered by each other. And that is based on various data, for example, by looking at the shape of cluster of galaxies, and we know that dark matter should not be interacting much more than a certain number. So again, what it is telling you is the dark matter is a weakly interacting object with the rest of us and also with itself. And again, that's how little we know about it. So given this situation, we are trying to switch our idea from machos to WIMPs. So in this case, WIMP is an acronym which tells you that they are very, very weakly interacting objects, even more weakly interacting than neutrinos we talked about before. And WIMP stands for weakly interacting massive particle. So they're supposed to be heavy, stable particles produced in the early universe. And heavy means mass is big, and because of m equal mc squared, that will take more energy to make. So we may not have had enough energy to make them in the laboratory so far, but the Big Bang had such an amount of energy that any heavy particle should have been produced, and some of them may be still left over. So this is the idea we will focus on for the rest of the lecture. And the idea is very simple. When everything is very hot and in equilibrium, you create this dark matter particle as many as any other particles we know. But as the temperature drops, then the dark matter should also come down in its quantity because the universe can no longer make them. There's just not enough energy to make them. But once there is dark matter there, the only way to lose it is the dark matter would meet each other and annihilate into some other particle species. So depending on how often they can meet with each other and annihilate, we know how much of that is left over. So that this curve shows how much may be left over depending on how often it would meet with each other and annihilate with each other. But once the universe becomes big enough and the dark matter becomes dilute enough, they would stop meeting with each other, so they cannot lose their numbers anymore, and then the universe is stuck with certain number of dark matter it has made already. So the dark matter is frozen. That's the word we use. And don't worry about these equations really, but this is a very simple estimate you can make about how heavy the dark matter particle may be if this idea of the WIMPs turns out to be the right picture, and that turns out to be about 300 giga-electron-volt. And this is actually a very interesting number because this is the kind of energy where the LHC experiment is right now studying. But at the same time, because dark matter is supposed to exist all around us, maybe we can actually capture them. But because dark matter interacts so little with us, it's very difficult to catch them. They pass through us all the time without us noticing it. So it's like trying to listen to a very, very faint sound in the midst of the metropolis like Manhattan. And of course, that looks totally impossible. So what we have to do then is to go to somewhere that's very quiet where we can shut out the noise. So where should that be? To hear the faint sound of dark matter, we have to go to a quiet space. But where could such a quiet space be? So that's the next question to you.